When you hear the term ballistic missile, you might wonder what the word ballistic means and what cruise means in the term cruise missile. What's the difference between the two, and how do they actually work? Ballistic is a physics term. Imagine throwing a ball as far as you can. After it leaves your hand, it follows a certain path through the air. A missile which follows almost a similar path is called a ballistic missile. Now, many people might think, how can we compare the path of a ball with the path of a missile that has a powerful rocket engine? This is where misconceptions arise. A ballistic missile actually travels about 90% of the distance to its target without any rocket propulsion, while on the other hand, a cruise missile travels almost the entire journey with propulsion. The rocket engine on the ballistic missile only fires for the first 10% of the journey. After that, the missile coasts toward its target.
For all, projectiles are objects that travel a long distance after receiving an initial push or thrust. They do not require any continuous force acting on them. Whether it's a thrown javelin, a bullet fired from a gun, or a shell launched from a cannon, there are only two primary forces acting on these projectiles during their journey: the Earth's gravity pulling them down, and aerodynamic drag from the atmosphere pushing against them. The term ballistics refers to the study of this specific path.
When we throw a ball to achieve maximum distance, we throw it at an angle. For short distances, assuming a flat surface, this path is often called a parabolic trajectory, governed by basic kinematic equations. However, for long-range ballistic missiles, calling it a parabola is actually a misconception. Because the Earth is spherical, the path of an intercontinental ballistic missile, or ICBM, is technically an elliptical trajectory. It forms an enormous ellipse with the center of the Earth acting as one of its focal points. A ballistic missile follows this elliptical path. For a ballistic missile, the initial thrust is provided by a rocket engine. To understand this better, let us look at its various stages. Let us say we are launching a ballistic missile to hit a target. The first stage is called the boost phase. This phase lasts only for about 1 to 5 minutes. The missile's rocket engines fire, pushing it to an altitude of about 50 to 400 kilometers depending on its range. It's worth noting that modern ICBMs typically use solid fuel rocket boosters instead of liquid fuel. Solid fuels are highly stable and ready to launch in seconds, whereas liquid fuels take hours to pump, a dangerous delay in modern warfare. By the end of the boost phase, the missile will be traveling at a tremendous speed, up to 6 or 7 kilometers per second. After this, the rocket booster is jettisoned and the engines shut off entirely. The next phase is the coasting phase. Traveling in the vacuum of space with zero air resistance, the missile uses the kinetic energy gained during the boost phase to coast along its elliptical orbit, reaching peak altitudes or an apogee of up to 1,000 kilometers. After reaching its maximum height, Earth's gravity pulls it back down, accelerating its speed. Once it falls below 50 kilometers, it enters the re-entry phase. Traveling at nearly Mach 20, or over 24,000 kilometers per hour, the missile hits the thick atmosphere. The friction is so intense that it literally tears air molecules apart, wrapping the missile in a sheath of superheated plasma. This plasma sheath blocks all radar and radio signals, meaning the warhead goes completely blind and silent as it plummets toward its target. During this phase, some fine adjustments can be made using small thrusters or fins. In fact, modern ICBMs use MIRV technology, which stands for Multiple Independently Targetable Re-entry Vehicles. This means one missile doesn't just contain one bomb. Its tip can open in space and release several different warheads to hit completely different cities at once. After hearing all of this, you may wonder, why not provide continuous propulsion all the way to the target? It comes down to a harsh physics principle known as the tyranny of the rocket equation, formulated by scientist Konstantin Tsiolkovsky. The equation is delta V equals VE times ln of m0 divided by mf. In simple terms, to make a rocket travel further, increasing its delta V, you need more fuel. But fuel has mass. If you add more fuel, the missile becomes heavier, meaning you need even more fuel just to lift the extra fuel. Because of this mathematical trap, nearly 90% of a rocket's weight is just fuel and oxidizer. If an ICBM used rocket thrust for an entire 10,000-kilometer journey, it would be too massive to carry any heavy weapons. By using the ballistic method, we let the physics of gravity and momentum do the work for free.
Now, let us take a look at what a cruise missile is. A cruise missile has continuous propulsion from the moment it is launched until it hits its target. Unlike ballistic missiles, they use jet engines and small wings, flying very much like a small unmanned airplane. The term cruise refers to the missile's ability to sustain controlled, guided flight at an approximately constant speed and altitude over long distances, rather than following a ballistic trajectory. Because they stay within the atmosphere, they can breathe in oxygen to power their engines, meaning they don't have to carry heavy oxidizers like ballistic rockets do. This makes them much lighter. They can also change direction mid-flight and fly incredibly low, sometimes just 10 meters above the sea. Because they imitate the curvature of the Earth, enemy radars cannot spot them until they're dangerously close. Cruise missiles navigate using GPS, inertial guidance, and a fascinating system called TERCOM, terrain contour matching. Satellites map the geography of the target area in advance. As the missile flies, it uses its onboard radar to compare the actual ground below with its saved 3D map, allowing it to navigate perfectly through valleys and around mountains. The main drawback of cruise missiles is their speed. Most are subsonic. Keep in mind, the speed of sound, or Mach 1, is not a fixed number. It changes based on air temperature and altitude, but typically standard jet engines cannot push past supersonic speeds. India's BrahMos missile is a notable exception. It uses a specialized ramjet engine to reach Mach 3, making it a highly lethal supersonic cruise missile. This brings us to the ultimate modern weapon: hypersonic missiles. Traveling at Mach 5 or faster, these are technically challenging to build. Standard jet engines melt or fail at these speeds. But hypersonic weapons are not just fast cruise missiles. There are two main types. First are hypersonic cruise missiles, HCMs, like Russia's 3M-22 Zircon. These use incredibly complex scramjet engines to maintain Mach 5+ speeds through the atmosphere. Second are hypersonic glide vehicles, HGVs. An HGV is launched into space by a ballistic rocket, but instead of following that predictable elliptical path we talked about earlier, the vehicle re-enters the upper atmosphere and literally skips or glides along the top of the air, making sharp, unpredictable maneuvers. Because it moves so fast and changes direction randomly, current anti-missile systems cannot calculate where to shoot it down. So far, Russia and China lead in this operational technology, while India is currently developing its own, the BrahMos 2. I hope this video has provided you with a better understanding of ballistic, cruise, and hypersonic missiles. These are just a few types of missiles in existence. There are many others, such as anti-ballistic missiles, which don't fall into the ballistic or cruise missile categories. Additionally, specialized missiles like anti-tank and anti-aircraft missiles serve unique purposes. However, ballistic and cruise missiles remain crucial classifications in the world of missile technology.